Welcome back from the break. Now we're ready to jump in to do the modeling of the internal combustion engines and look at how it interacts with the other type of model. So we get engine efficiency and some high-level modeling of engine efficiency. So what we have right now is that we have covered the driving mission with the power requirements, so we know what happens outside the wheel, and we will start working with the components that we see in the powertrain that is used to convert the energy from the combustion engine and transform it to, or we will have an electric machine and the transmission components that are there. On the third lecture I will go into this picture in more detail and discuss what the different markings here means, but right now we're focusing on the combustion engine that will be used in a driveline to get the power out to the wheels and out to the driving mission. So we will cover combustion engine as prime mover now, then a little bit later we will look at the electric machines and generators, and then we'll look at energy storage with batteries and supercapacitors, and finally some glue components that are used to connect mechanical things together or electrical things together. Jumping into the combustion engine, we have the two ways of modeling. We have the quasistatic approach and we have the dynamic approach. In the quasistatic approach, it is the requirement that comes from the driving mission that has propagated through the driveline. So we have a given rotational speed and we have a given torque that reflects the demand that we have from the cycle. In the dynamic approach, we are injecting fuel, and the combustion engine is coupled to the driveline. So the driveline, together with the internal combustion engine, determines the rotational speed. The engine cannot determine the rotational speed itself, and the engine will influence whether we are accelerating or decelerating in the cycle. So we have an interplay here that is taken care of by the connection to the driveline. And when we look at it from the power perspective, we have the chemical power flow here, P for power, C here for chemical, so it's the chemical energy that we have in the fuel. And that is what we are giving as input to the combustion engine in terms of the utilization. That is what it's consuming, and what it's producing is the power output here. So the efficiency then becomes the useful power divided by the provided power in terms of fuel. And the enthalpy flow of fuel, the fuel power, is the same thing as the lower heating value of the energy times the mass of the fuel flow, the fuel mass flow that we have. Then we get the chemical power that we are supplying to the engine. So in the QSS part, we can take the power that comes from the driving mission propagated through the combustion engine and get to know the fuel power and calculate the fuel flow. And with the fuel flow we can then integrate that to total mass of consumed fuel, and with the density we will get the volume consumption of fuel if we're thinking about liters per 100 kilometers or equivalent. So now if we look at this efficiency using something that's called brake specific fuel consumption, which will be essentially proportional to 1 over the efficiency. That's a popular way of presenting combustion engine efficiency if you come from the combustion engine side. And when we're talking about engine and when we're talking about vehicle design, we have to communicate between the groups. So we have to understand the language of the engine guys, and we have to understand the language of the chassis guys, and we have to understand the transmission guys, especially if we are working on optimizing the total system and is responsible for function development of energy optimization. So looking now at the engine efficiency, we have the following representation of the brake-specific fuel consumption, which is a constant divided by the engine efficiency. So the lowest value that we have in the fuel consumption is here, which is directly then proportional to the highest efficiency. So here we have the sweet spot of this particular engine, and then the efficiency decreases when we go to lower and lower loads. So the fuel consumption increases when we go to lower and lower loads. And the shape that you can see here is that we have a slight inclination with the engine speed, and this comes from the engine friction. And the raggedness you see here is due to measurement noise and measurement uncertainties. But the general trend here that you should observe in most of these fuel consumption maps is that there is a convex behavior of these lines of ISO efficiency or ISO brake-specific fuel consumption in this case. And this comes from engine friction that has an engine speed dependence that increases with the friction increases with engine speed. And when we go down here, you see that we've cut off the axis here at 2 because the lines go to infinity when we go to 0 torque out, because then at that point the efficiency is 0 and we would get division by 0 in the brake specific fuel consumption domain. So this is used very often for fuel consumption assessment. So we have engineering perspective in design and evaluation, and the engineering perspective here is that we're using it in the design and in the evaluation of different concepts. And when we're doing new concept development, we would need to know how does the new concept respond in this situation. So what do we do when the map data isn't available? For example, we're working with a pre-design when we don't know yet exactly how the engine, or maybe we're asking how should we design the engine for this particular vehicle. And the same approach and the same thinking could be applied to if we're looking at an all-electric vehicle and we're wondering about how to apply a certain electric machine or what electric machine to select for that particular operation. So for engine size, we will use some things that are common in the engine domain, and we will first introduce two normalized engine variables. One normalized engine variable is the mean effective pressure, and the definition of a mean effective pressure is that we take the work and we divide it by the displacement volume of the engine. So this is work production normalized with the size of the engine. And this is pretty nice because we know that bigger engines will produce more work. So this is a way of normalizing the engine and getting numbers that are comparable between engines of different sizes. And it's work here that we take the mechanical work, or we take other work, which is the same thing as energy divided by displacement volume. So when we do the calculation, the energy or the work that we're producing with the engine is the integral of the torque over the revolution. So this is the work per one cycle, and this is the displacement volume that we have available to it. This could be used to define also other energy. So if we don't look at the mechanical torque here or the work, then we can use another type of energy, for example the fuel energy. So we can also use for energy comparisons. We can also use it for energy comparisons, like we can work with something that's called fuel mean effective pressure. So we can use fuel mean effective pressure, we can use the brake work, then we get the brake mean effective pressure, and we can compare them to each other, and we will do that in a few slides to come here. So this is one domain, or this is one dimension. It's a load dimension. The other is a speed dimension. If you look at the map that we had, let me back off to it once again. So here we have one dimension which is the speed, and here we have another dimension that is the load. And here you already see the brake mean effective pressure that has been normalized. So it's torque up here, so high load up here, and low load down here, and engine speed here, low speed, high speed. In these two domains we have the mean effective pressure for the load domain, and we have either engine speed, or in this case the mean piston speed is a normalized engine speed variable. And the mean piston speed is a dear child with many names. So we have SP, CM, or MPS. That's variations of the same concept that is used in the literature depending on who's the author. And here we're looking at the angular velocity of the piston. We're normalizing it with rotations, and S is the stroke length. How far does the piston travel? That's the stroke of the engine. So we're looking at how fast is the piston traveling in average over a cycle. So then we're normalizing it towards a velocity that will be related to the speed of sound. So we're not working with Mach numbers, but in a sense similar to that thinking that we would like to capture whether or not we are close to reaching sonic conditions at some place inside the engine. And then the mean piston speed is a good variable to describe that behavior, to describe that phenomenon. So we have normalized engine variables. So the engineering perspective of using them is that if we can build a good model in the mean effective pressure domain and the mean piston speed domain, then we can scale it with the displacement volume and get a generic engine model that we can utilize to scale up, scale down, and investigate different impacts of our design on the fuel economy. So this opens up the possibilities of sizing engines for optimal fuel economy for a vehicle, etc., or optimizing performance requirements for a vehicle and balancing that against the efficiency. Other use cases is that we can compare performance for engines of different sizes, and rules of thumb for engine sizing is that at maximum engine power the mean piston speed is 17 meters per second, and a naturally aspirated engine reaches a mean effective pressure of about 1 megapascal. So from these we can get the engine size, and we can get the connection to engine power and size. So we can connect the dimensioning variables together through these design variables. So looking at the engine BMAP, so this is output energy and this is input fuel energy normalized to each other. So here we have normalized them for measurement data of an engine where we see that there's a fairly clear trend that it's fairly linear with respect to load. So the relation here is an affine connection, and this type of affine connection is sometimes called Whelan's line. So it's a line with an offset. So we have a line here with an offset here. That's the Whelan's line. And the engine efficiency is then the slope of the line that goes from the origin out to a certain point. So at this point here, the efficiency is directly proportional to the line that goes through the origin and this point. And when we have zero output torque here, we have zero efficiency, and here we have negative efficiency because we are injecting fuel, but we're not getting any work out. Actually, we're needing work to keep the engine alive. So this is engine braking down here. And the most effective point, the most efficient point is up here, where we have the highest slope. So if we try to lay a line that touches the top point here, then we see which of these measurement points had the best engine efficiency. So we can look at the slope, which is this, and we can look at the offsets and see how they depend on the engine operating conditions. And that's the thing that we have in the next slide here. And this comes from the book, where they are showing that they have seen the maximum efficiency has been in the maximum slope has been in the mid-range, while the friction losses are higher at higher speeds. So we have a decrease here in terms of the efficiency. So the trends in between these and the scaling with the engine speed will give us the best operating points that are up here. So this is a way of working with the dimensioning of the engine and using it to get the efficiency out. And when we come to the next point, which will be electric machines, we will come back to these kind of maps that you have seen for the combustion engine. That one will also be visible for the electric machines. So now we look at electric motors and generators and a little bit on the modeling. So we will look at the electric motors. They are often classified into 4 groups. There are other classifications too. We have DC machines, synchronous machines, sometimes including brushless DCs, asynchronous machines, switched reluctance machines, and stepper motors that are digitally controlled synchronous motors. And for those of you who might be interested in photography, know it's about ultrasonic motors that are using piezoelectric effect to drive them. But they are very fast. So when we talk about electric machines, we have 4 quadrants. One quadrant is the driving quadrant, and one quadrant is the braking quadrant. And this is when we're going forward. If we go backwards, we have the opposite. So we go backward with negative torque, we are driving the vehicle backwards, and when we're going backwards but with positive torque, we are doing braking in the reverse direction. So when we look at electrical machines and hybrids and hybrid electric vehicles, you have separately excited DCs, you have permanent magnet synchronous DC machines, you have induction motors, and switched reluctance machines. The interest in switched reluctance machines comes from the interest to not use rare earth metals like neodymium magnets. AC motors compared to DC motors, they are less expensive, but will require more sophisticated control electronics that can give higher overall costs. And we have higher power density and higher efficiencies in them. So when looking at AC motors and looking at those that are available in the advisor database, the permanent magnet motors have an efficiency of 92.5% and a power density of 660 watt per kilogram, while the induction motors have lower efficiency, but they are a little bit more compact. So if weight is an interesting part, then that's it, and if efficiency is the dominating thing, then that's the selection. So when we look at the electric machines and adopt the quasistatic thinking, we have the delivered power, that is T2 times omega 2, which is the input power. So the power relationships relate to the delivered power and the input power, and the relation between them depends then upon the efficiency. Then defines whether we're using it in the machine direction or if we're using it in the generator direction. So we have the usage will depend The efficiency definition will depend on if we're using it in the motor direction or if we're using it in the generator direction. And here we have the quadrant, so up here we have the motor direction and down here we have the generator direction. And I incorporated this here so that we'll see that the efficiency lines need not be identical for the motor direction versus the generator direction. Usually in traction motors we design the machine for being good in the forward direction, so in the motor direction, and then we take what we get in the regenerative direction. So we can describe the efficiency either as lookup tables, and here's another example where we only have the data on the positive side, and one can use Whelan's line approaches to capture the low power performance. But this is something that you encounter when you work with electric machines, so this is something that you should get acquainted with. And we see the peak efficiencies here that are 96% here, and here it's 90%, but the evolution continues steadily to increase. We have also here in the first quadrant maps for AC machines. We have a permanent magnet synchronous machine where we have imposed the torque limitation, and here we have an asynchronous AC machine where the maximum torque limitation is imposed here, and we see the efficiencies of them at different regions. So traditional first quadrant drive is normally well documented when you're using it as a traction motor, and you can quite often get access to supplier information for the machine in terms of the efficiency, and we use it for the electric motor drive, and we would like it to use it in the hybrid vehicle also for the generator side. But when we only have this, how do we determine this here? One method is to mirror the efficiency map that you saw that might not be good enough, so we take the efficiency of the generators equal to the efficiency of the motor side, but with the negative torque here, so we're just doing a mirroring. Or we calculate the power losses that we have in the machine, and then we mirror them over. We calculate the power losses that give rise to the efficiency, and we mirror them onto the braking side. Or we use a Whelan's approach with the loss line that we use to extrapolate over to the negative side. So, as I mentioned previously, as I showed you, mirroring the efficiency might not be perfect. Motor modeling. There are more advanced models where you use component knowledge, inductance, resistance, and build physical models. And the dynamic models are developed in the book. And some examples of motors in the devices near us are a regular DVD player that, if you take it to pieces, it has 3 different types of motors. It has a normal DC motor for opening and closing the tray. It has a BLDC motor for rotating the disc. A BLDC is a brushless DC motor that is essentially a synchronous machine that can be controlled with a special device. So it gets to act with the control system to act as a DC motor. And in it, it's a stepper motor also for controlling the position of the laser head, so that the laser head will get its most accurate position. And after this, I think it's a good point to take a second break so that you can refresh yourself and get blood circulation into your body and get ready for the next module. So take a break and see you back then.